So when we have this notion of context, going back to that illustration where we have the people we see on a regular day in our lives, and we start drawing lines between people, right? So by drawing these lines, we're trying to represent those interactions between different individuals. Well, those interactions are connections. These connections is what we are going to consider context, right? And you can also realize that this context may differ from the context of one pathogen to the context of another pathogen. If we are comparing a pathogen such as the bacterium or the virus for an airborne disease, well, in the context of airborne diseases, these pathogens are traveling through the air in small particles, right? And it's a matter of releasing these particles into the air and catching some of these particles while they are in the air or while they land on a surface, right? And so in that context, a contact is going to be an opportunity to be close enough to somebody to either sneeze, cough, or breathe from each other. But if we are comparing an airborne disease with, for example, a sexually transmitted disease, there in that context, the contact will be very specific. The contact will have to involve a sexual encounter between the two hosts, right? So the definition of contact may vary significantly from one context to another context. But importantly is, once we are in one context and we have a definition of what a contact is or what a contact may involve, then we may consider how individuals are having contacts with each other, and we can represent those individuals in a certain way. And here's one way of doing that representation. That representation is giving a visualization, or at least is a theoretical means of representing the structure of contacts. The structure in a population, but specifically the structure of contacts, which is pertinent for infectious diseases. So if you represent every individual with a circle or a dot, and if you represent potential contacts or potential transmission with a line, then you may end up with a figure that looks like this. This is, in mathematics, this would be called a graph. That is a well-known branch of mathematics dedicated to the study of these things, these graphs, and it's called graph theory. Outside of mathematics, outside of mathematics, you would probably come across with literature in which this is called network science. So this can be called a network, or it may be referred as a graph, right? And there is plenty of literature and theory about this. This is a visualization of a network or a visualization of a graph, and this, in the context of modeling infectious diseases, this has to do with the word mixing. Okay, mixing is how individuals are pairing with each other, how they mix with each other, how they are interacting with each other. And when there is a very well-defined structure of contacts, right, something that may be visualized like this. Here's another example of another structure of contacts. This is referred as heterogeneous mixing. Okay, we will go in detail about the epidemics on social networks or infectious diseases on social networks. We will do that at a later time in this class. But I just would like to mention. I would like to mention heterogeneous mixing because the other type of mixing, which is the one we will start with to write down some equations, the other type of mixing is mixing that is not heterogeneous. It's called homogeneous mixing. So this is a context in which you may think of individuals in the population, say individuals in the population are represented by some particles, and you want to kind of make an analogy between these particles and maybe some homogeneous solution. So if you assume that the particles in this population have the ability to mix very well, this mix will be so well that it will be homogeneous, right? So an example of Homogeneous mixing is a solution of sugar with water. So you pour sugar into a container and then start putting water, and you start stirring that container, and pretty soon you will not be able to tell, right, where the particles of sugar are, because they mix so well with the water, right? And this is a cartoon representation of that type of scenario. When we refer to homogeneous mixing, we're referring to a population in which individuals and particles in that population are not really displaying a particular pattern. Okay, so in a way, this well mix means that particles are equally likely to encounter each other because they are so well intermixed, right? But this idea of homogeneous mixing, and I'm using some words here like equally likely. Equally likely means the same chance, right? And equally likely the same chance, that is connected to a word in mathematics that's uniform. Uniform from the point of view of the uniform distribution. Okay, in the uniform distribution, things have equal chance or are equally likely. So homogeneous mixing typically is also known as random mixing, and is the type of random that is uniformly at random, unbiased, right? So the mathematical models that we will derive first are models that use the assumption of homogeneous mixing, okay? And then later in the course, we will develop some mathematical models for heterogeneous mixing by means of social networks. And this concludes our introduction to mathematical models of infectious diseases.